Lecture 6 covers sections 2.8 and 2.9. At the end of today's lecture, you should be able to identify an ideal gas and apply the ideal gas law. You should also be able to determine when the ideal gas law is applicable based upon reduced temperature and reduced pressure. For us to begin, let us talk about valence bond theory, that is our intermolecular potential energy, E sub r, as a function of our intermolecular distance, r. And this is typically modeled by the MI model. Now, if we look at our graph, we have our intermolecular potential energy on our y-axis, and on our x-axis is our intermolecular distance, r, expressed in picometers. That is the distance in between two molecules. If we look at our graph starting from the right, we can see when we have two hydrogen atoms existing at a very far distance that there's going to be no interaction between these two molecules. That is, the electrons will not be attracted to the opposite protons. And in this situation, we don't have to consider the description of our intermolecular distance between each atom or molecule as a probability distribution function. That is, they are behaving independently of one another. Now, as our intermolecular distance begins to decrease, our molecules begin to interact. That is, the electron of our left hydrogen molecule will be attracted to the proton of the right, and vice versa. Now, there's a trade-off between attraction and repulsion. As these two molecules get closer to one another, they will begin to attract as well as simultaneously repel. The protons will want to push away from one another, but the electrons will want to attract towards the protons. Eventually, once we reach a distance called the bond length, these two hydrogen atoms or molecules have now combined. And we'd have a global minimum of our energy. If we try to push these molecules any closer, they'd experience a very strong repulsive force. Now, there exist a few situations where our intermolecular potential energy is a global minimum and zero. Our global minimum is when these two molecules bond together, and it's at zero when they are very far apart. Now, we used hydrogen as an example. However, this could constitute any gas. Now, for us to not consider the attractiveness of each molecule to one another, we are going to assume that at low to medium densities, our intermolecular distance r is very large. And if r is very large, our intermolecular potential energy, E of r, is going to be zero. That is, our molecules are going to behave independent of one another, and we don't need to describe each molecule's position in relation to all the other molecules using a probability distribution function. Thus, at low to medium densities, the gas is going to behave in accordance to the ideal gas law, which is stated as the pressure of your system times the volume of your system is equal to the number of moles within your system times your universal gas constant times your temperature. Or your pressure times your specific volume on a molar basis is going to be equal to the universal gas constant times your temperature. Now, N, which represents the number of moles within your system, is equal to the mass of your system per your molecular mass, capital M. And R bar is your universal gas constant, taken as 8.3145 kilojoule per kilomole K. Now, we can relate our gas constant of a specific gas R to our universal gas constant by dividing our universal gas constant by our molecular mass. That is, R would be equal to R bar per M. Now, if we substitute N into our expression for ideal gas, we can say our pressure times our volume is equal to our mass times our specific gas constant times our temperature. Or our pressure times our specific volume would be equal to our gas constant times our temperature. Our pressure is taken in kPa, our volume is taken in meters cubed, our mass is kilograms, our gas constant R is kilojoule per kgK, and thus T has to be expressed in our absolute temperature scale, Kelvin. Do not express T in degrees centigrade. That will violate homogeneity. Table A5 provides the properties, namely our molecular mass and our gas constant for various ideal gases. We see at table A5 we have a heading, Properties of Various Ideal Gases at 25 degrees centigrade and 100 kPa. And we have gases, our chemical formula, our molecular mass expressed in kilograms per kilomole, our gas constant expressed in kilojoule per kgK, our density, our constant pressure specific heat, our constant volume specific heat, and the ratio of our constant pressure to constant volume specific heat. Now note these properties are taken at standard temperature and standard pressure. Can they be used for a pressure greater than 100 kPa? The answer is oftentimes yes. Since our gas is low to medium density, we assume that pressure is not affecting our system. Thus, if our pressure is going to be low enough, which we will quantify shortly, we can use these values at elevated pressures. If you consult table A2, we can always calculate R based upon your universal gas constant and your molecular mass taken from table A5. Now, table A2 also provides our critical constants, i.e. our critical temperature and critical pressure, that reflect our critical point on our PT diagram. Now, table A2 lists your substance, your chemical formula, your molecular mass, your critical temperature, your critical pressure, and your specific volume corresponding to your critical temperature and pressure. Now, let's consider a system that is a control mass. That is, the mass at state 1 is going to be equal to mass at state 2. And we want to determine our pressure at state 2 in terms of our pressure at state 1, our temperature at state 1, our volume at state 1, our temperature at state 2, and our volume at state 2. For us to do this, we are going to write out the ideal gas law for state 1. P1V1 is equal to M1 R1 T1. Or our mass at state 1 is equal to our pressure at state 1 times our volume at state 1 per our gas constant per our temperature at state 1. Now, at state 2, we can express our mass in the same formulation. Our mass at state 2 is equal to our pressure times our volume per R times T. Since our mass is constant and our gas constant is constant, we can say our pressure at state 2 would be equal to our temperature at state 2 per our temperature at state 1 times our volume at state 1 per our volume at state 2 times our pressure at state 1. Later, we are going to introduce a term that quantifies how we move from state 1 to state 2, i.e. a polytropic process. And we see our ideal gas law is going to obey the formulation of a polytropic process.